Hi everyone. In this video, I'm going to cover a topic that often seems really intimidating to people the first time they see it. And that is determining the end behavior and intercepts in order to graph a polynomial. So I'll say up front in this video, we're not looking for the perfectly exact graph of a polynomial. We're looking for the general shape of it here. Okay, so don't panic if every last point isn't perfectly graphed. We're mostly looking for the general idea of how the graph is going to behave. Okay, so let's first talk about in behavior. Okay, so if we let f of x here be a polynomial of degree n, all this is saying is like you have a polynomial of degree m, where n is 3. The leading term would be some number times x to the third. Okay, or if you have a degree 7, it would be some number times x to the seventh, followed by potentially a bunch of other terms after that. Okay, but the largest term will be of degree n. So we're going to let this be a polynomial function, and the end behavior of the graph of this function, f of x, is going to be determined by these following cases. So in this first case, we have n being odd, okay? So we have a polynomial of degree n, where n is an odd number, and our leading term is greater than 0, so it's a positive number. Then the graph of this function, we say it falls to the left and it rises to the right. What this means is as we go off into infinity to the left, the graph is going to go off into infinity, or off into negative infinity. Okay, so as we go into negative, as we go off to negative infinity, the graph of the function is also going to go to negative infinity. And as we go to positive infinity, the graph of the function is also going to go to positive infinity. Okay, so you can tell this just by looking at that leading term. Okay, that's that first term of a polynomial. So an example here is if we just have the polynomial x to the third all by itself. Okay, so we know this is the general shape of it. This is a really simple, really straightforward example of what that's going to look like. So case number 2 is where n is some odd number, and again, but now a sub n is less than 0. So the leading term is negative. Okay, then the graph is going to rise to the left. So as we go to negative infinity, the graph of the function is actually going to go to positive infinity. Okay, and as we go to positive infinity, the graph of the function is now going to go to negative infinity. Okay, so we say this rises to the left and falls to the right. And another example of this is f of x equals negative x to the third. Okay, so really we're just looking at the negative of our previous example. Another case is where n is now an even number and a sub n is greater than 0. And in this case, the graph is going to rise to the right and fall, and rise to the left. Sorry, to the right and to the left. So as we go off to positive infinity, the graph is also going to go to positive infinity. And as we go to negative infinity, the graph is still going to go to positive infinity. And an example here would be f of x is equal to x squared. All right. Another example, lastly, is where n is again an even number, but this time our leading coefficient is less than 0, so it's a negative number. Then the graph is going to fall to the left and fall to the right. And a really simple example would be just the negative of our previous example. F of x equals negative x squared. So as we go to negative infinity, the graph of the function is going to go to negative infinity. And as we go to positive infinity, again, the graph is going to go to negative infinity. So this is how the end behavior is going to look. All right, so now what we can do is we can now examine the behavior of a graph at the zeros, okay? So if you're given a graph where it's all, or if you're given a function where it's relatively easy for you to find the zeros, this is a pretty simple task. If c is a 0 with odd multiplicity, which remember we talked about that in a previous video, if c is a 0 with odd multiplicity, then the graph crosses the x-axis at c. Okay, so we're going to do a couple examples here in a minute, so I can show you what this looks like. But we know that the trace of the graph, if we're drawing out the graph, it's going to cross at c. And if c is a 0 with even multiplicity, then the graph touches the x-axis but does not cross at that 0, c. Okay, so it touches but does not cross. That's if it has even multiplicity. So here, let's go ahead and take a look at this function, f of x equals x times x minus 2 times x plus 1. So the first thing we want to do is look at our leading term. Now, be careful. this is not your leading term here. This polynomial has been factored. It is not of the form f of x equals a sub n to the times x to the n plus a sub n minus 1 times x to the n minus 1. So you need to put it in that form. But the good news is you don't actually have to FOIL this function out entirely, okay? All you have to do is think about if you were to FOIL all of these together, what would your highest degree term be? In this case, we would have x times another x, and then times that x again, because we have x times x minus 2 times x plus 1 times x plus 1. So if you were to FOIL all of those out, your highest degree term would be x to the fourth. It'd be x times x times x times x. And to see why this works, it may be helpful for you to maybe do one of these just one time so that you know exactly how this process works. If you haven't done multiple of these together, it might be helpful for you to see how that looks. Okay. So now that we have the leading term, we can determine the end behavior. So we know that the end behavior is determined by the exponent here and by the sign of the leading coefficient. Well, we know the sign of the leading coefficient is positive, okay? And we know that the exponent is even, okay? So the exponent is even. All right, so let's see which case we have here. If the exponent is even, n is even, and a sub n is greater than 0, so the leading coefficient is positive, the graph is going to rise to the right and to the left. So we know the end behavior will rise to the right and to the left. Okay? All right, so now what we're going to do is we're going to look at our zeros. All right, so our zeros here are going to be given by x equals 0 from this one. We're going to have x equals 2. That's another 0 from this one here. And we're going to have x equals negative 1 from here. And their multiplicities are 1, because we have just one instance here. X minus 2, there's just one of those, so we're going to have a multiplicity of 1 again. And then x plus 1 squared, that means we have a multiplicity of 2 for negative 1. So let's go ahead and graph each of these zeros, and we'll determine what happens at each of these points. So let's graph the 0, 0. All right, so we have 2, and we have negative 1. Okay, so the first thing we want to do if we actually want to graph this now is go back and look at our end behavior now that we've graphed all of our zeros. And we know that it's going to rise to the right and rise to the left. So this is the last, this 0 here is the last time it's going to interact with the x-axis at all as we go to infinity. And this 0 here is the last time it's going to interact with the x-axis as we go to negative infinity. So we know that the general shape of the graph is going to go up as we go further to the right from here, and it's going to go up as we go further to the left from here. Okay? And now we know at the 0, negative 1, because it has a multiplicity of 2, looking at our previous rule, where C is a 0 with even multiplicity, where 2 is even, then the graph touches but does not cross at C. Okay, so it's gonna touch here at negative 1. Okay, it's going to touch at negative 1, but it's not going to cross. So that means it's going to have to go back up and then back down when we get to this next one. But we know that since at 0 has a multiplicity of 1, that means there is an odd multiplicity. Therefore, it's going to cross the x-axis here. So it'll go up, and then it'll cross here, and then it'll come back up to here. And if we did this right, then we'll know that it should cross here as well. Okay, which at 2, we have multiplicity of 1, which means it's going to cross as well. Okay, so this is going to be the general shape of your graph. This is probably not the best graph I could have drawn here, but this demonstrates the basic shape of the graph. Okay, so let's take a look at another example. Here we have g of x is equal to negative, or you can think of this as negative 1 times all of this, x minus 2 times x plus 1 squared times x minus 1 squared. So let's think about our leading term here. Okay, so if we were to FOIL all of this out, we have just one negative sign here since all of these are positive, so there'll be a negative sign. All right, And then we have x minus 2. Then we'll have x times x plus 1 times x plus 1 again, times x minus 1 times x minus 1 again. So our leading term is going to be x to the fifth. All right. And if you want to see how this works, it might be helpful to go ahead and FOIL all of this out. That way you can see that this is indeed x to the fifth. But really what you can do is you can kind of just count the incidence of each of these x's out front here. Okay. So now that we have the leading term, we have that it is a polynomial, or it is a polynomial with a leading term with an odd exponent and a negative leading term. Okay, so if odd exponent, let's go back on our rules. So n is odd and a sub n is less than 0. Okay, that means that our graph is going to rise to the left and it's going to fall to the right. So it's going to rise to the left and fall to the right. Okay, so let's look at our zeros. So here we have x minus 2, so that means that 2 is going to be one of our zeros. We have x plus 1, that means negative 1 will be one of our zeros. And we have x minus 1, so 1 will be one of our zeros. Okay, so now let's look at the multiplicities. So x minus 2 only shows up once with an exponent of 1. Therefore, we're going to have a multiplicity of 1. X plus 1 has an exponent of 2. Okay, so negative 1 is going to have a multiplicity of 2. And x minus 1 shows up with an exponent of 2. Therefore, we're going to have a multiplicity of 2 here as well. All right, so we can go ahead and plot these points. So we have a 0 at 2. We have a 0 at 1. And we have a 0 at negative 1. Okay. So we know, again, let's look at our end behavior. So it's going to rise to the left and it's going to fall to the right. So let's go to our furthest 0 on the left, which is here. And we know that from here on, it's going to rise. It's going to go up. Okay? And then if we go to our furthest 0 on the right, which is here, it's going to fall. All right, so at the 0, negative 1, it has a multiplicity of 2. Okay, so that means it's going to touch but not cross. So we'll have to go back up and then come back down to hit this 0 here. And that's at 1, which again has a multiplicity of 2. So that means we're going to have to touch again but not cross. So we can go back up and then back down, where it's going to cross again to give us this basic shape. Again, not the best drawing of a graph, but I wouldn't expect you to draw this perfectly. This showed up on the final. So that would be a good way to draw this graph here. Again, it just demonstrates the basic behavior. It's not overly complicated. It's not perfect, but it does show the general basic behavior of the graph. In reality, we don't necessarily know without plotting more points here how exactly high each of these are going to go, or how quickly it's going to rise to the left, or how quickly it's going to fall to the right without plotting more points. And you can feel free to do that if you want a more accurate graph. But this section is really just about capturing the basic behavior. Okay, so these are a few of the principles to follow when graphing some of these polynomials.